statistical view again will be that the non-specific condition, that both plant load and maturity are of primary importance. The molecular basis for the inflammation in gingivitis is still fairly poorly understood. Clearly, LPS from gram-negatives has a primary role, and toxins from some of the bacteria may be involved. We know that the host cells can recognize the bacterial component via toll-like receptors, and in that way activate NF-kappa B, the central inflammatory pathway. Most people have looked for specific interactions in that way. I think an important aspect of this is microbial load. I think that's probably under-investigated. My former colleague Julian Maglick has done, King has done some really nice work on Candida and how epithelial cells can recognise when Candida goes from its yeast form to its hyphal form. And he identified the particular receptors that do that. And not only is it that yeast to hyphal form, it's also numbers. The epithelial cells can quorum sense the level of the biofilm above it. And so we're pretty sure that a similar mechanism will be found from gingivitis. So the host cell can just recognise when numbers have got above a particular level, and that triggers inflammation. So we wanted to look at this in more detail. This is a paper published a couple of weeks ago from my group, formed by my student James Kistler. And we wanted to ally the classic Harold Lowe experimental gingivitis model with state-of-the-art next-generation sequencing to characterise the community. So we were going to monitor the changes in plant in individuals who withdrew from oral hygiene for 2 weeks, and also specifically identify any health and disease-associated taxa. So we had 20 individuals who are periodontally healthy. We gave them a stent to wear when they were brushing their teeth, so they abstained from brushing their mandibular teeth for 2 weeks. To give the data some context, we also got samples from a group of chronic periodontitis patients, just to see if we saw big differences between the health and periodontitis groups. This was the experimental design, so we took samples at baseline for 1 week and 2 weeks, and we also took GCF samples, although we have yet to complete the analysis of the inflammatory markers in those. So this was the clinical data. As you would expect from baseline in a healthy group, we had 6.7% of sites with visible plant. Obviously went up to 62.4% with withdrawal of oral hygiene, and 87% at 2 weeks. And the number of bleeding sites went from 7% up to 37%. So all of the individuals suffered from a clinical gingivitis by the end of the study. For the microbiology, we identified nearly 400,000 sequences, which we identified to a 98.5% sequence identity level, and we used the HOMD reference database as the sequence identification. Even in these healthy sites, we found a range of between 90 to 400 species per sample, with a median of 299. So even in a very healthy site, no visible plant, we were finding 300 different species. We were surprised at how diverse the community was, even at baseline. Also, what was interesting when we looked at the communities that we found and clustered the whole samples together, was that we confirmed what others have found, is that every individual at species level has their own characteristic community. In fact, we can almost use that for forensic purposes. If I took a saliva sample from all of you now, we did the profiling, and then in a month's time, one of you gave me a sample, I could probably tell which one of you it was. There's that much discrimination in the individual profiles that people have. And in general, in the absence of systemic antibiotics, oral say, salivary community profiles are actually pretty stable from month to month in adults. And so you can see here that the primary clustering was by individual. So this is individual 8 at baseline 1 week and 2 weeks, individual 4, individual 16. And so although there was a change, differences in the communities going from baseline to 1 week and 2 weeks, the effect of the individual was actually the strongest determinant on the composition of the microbiota. So we can also look at the data by principal coordinates analysis. So this represents each individual sample in multi-dimensional space. So this is the baseline. This is at 1 week, so you can see we're getting a shift toward the right there. And then that's 2 weeks. So you can see, although the communities are different, they're all shifting in the same direction in the 3D plot. If we superimpose the periodontitis, that looks at first as though they're interspersed around them, but in fact if we spin the figure around, that they're in front on the previous figure, they're going off in a different direction. So, a bit oversimplistic, but it suggests that periodontitis is not a continuum in that gingivitis, it's a whole different community that you have in those patients. We then analyse the data to look for specific associations. We show that the Rothia, some of the streptococci and actinobacillum were health associated. Fusobacterium is well known as a gingivitis-associated organism. Its numbers are well known to go up as plaque accumulates. And Campylobacter has also been shown in the past. But the Gemella and Lautropia are new findings. It perhaps gives some credence to the data and this method of analysis that the organism most strongly associated with periodontitis is Porphyromonas gingivalis, confirming lots of previous work. Perhaps a bit more surprising was that Prevotella denticola was there. I gave this talk in Japan a couple of months ago, and somebody very politely came up and I think there's a mistake on your slide. You really meant Treponema denticola, didn't you? But I don't think it is Prevotella. And in fact, other people have found this. The group Anila Kumar in Columbus has done similar work in large groups. She also consistently finds that Prevotella denticola is a disease-associated organism in periodontitis. And so we're now going on to do further studies to look at how these organisms interact with epithelial cells and for the health-associated species to see if any potential that they might have for possible probiotics. So if we go back now and move on to periodontitis, this is Csikszentmihalyi's classical work where he identified that when you look at the most diseased sites, there's a significant association with Porphyromonas gingivalis, Treponema denticola, and Tamarala forsythia. And so this work all led to what we might call the specific plaque hypothesis. But I think increasingly people are having some problems with the specific plaque hypothesis because it really depends on a pretty conventional view of host-parasite interaction. And it really applies to what you might call the classical infectious diseases. So something like diphtheria. If you catch diphtheria, then Corynebacterium diphtheriae will colonize your throat, damage you and give you the symptoms. And with that, with one species, one disease, you can reproduce Cox postulates easily. What we have here is a complex disease at a mucosal surface in the context of a very highly complex bacterial community, and so it may not conform to this modelling. So what people are thinking is maybe because we are naturally colonized with so many bacteria that hopefully are healthy, that there's a normal homeostasis, and maybe disease is when that homeostasis starts to break down. And so maybe it's the amount of information for a given challenge which is important. And so some relevant work to this, I think very interesting work has come from Tom Van Dyke in Boston, who's been looking at part of the the natural history of information, if you like. And what he's shown is that resolution of information is an active process. You might think, that you get an insult, you get information, and that just dies away. But it doesn't. There has to be something to actively stop the information. And Tom suggests that periodontitis may be a failure of resolution just as much as a feature of excess information. And so he's identified mediators of information resolution, which have been termed the resolvins. And this study is very interesting. This was the rabbit ligature model, where there were two groups of animals. Both were provoked into periodontitis by tying the ligature around the neck of the teeth, but one group were given the resolvin. the RVE1 resolving. And then after the treatment period, they looked at both clinically and microbiologically. The treated group, sorry, the control group first of all, but they had the periodontitis, but hadn't had the treatment, had a normal or what you might say is an analogous to a rabbit version of the periodontitis flora. So there were versions of the pathogens that you'd expect to see. Whereas the resolving treated animals had a normal, healthy microbiota. So they'd started out with disease, but just by treating the inflammation had changed the microbiota. So no antimicrobial, just resolving the inflammation, and the pathogens that had been there were no longer predominant. And then in another study, Antana in Boston did this study, a longitudinal study, looking at the very early stages of periodontitis in either healthy or what she called slight periodontitis subjects. They were monitored for 18 months. Out of that 117, 22 broke down, and in those the pathogens were detected. But when she looked at the time history, she never saw the pathogens before the disease. So breakdown, inflammation of the periodontium occurred before the numbers of the organisms were raised. So it would appear then it's a complex relationship between the host and the microbiota that's important. And there may be some defect, which means that those individuals who are susceptible get too much information for the degree of the challenge. And so what's relevant to this is this new hypothesis put forward by George Atchison-Gellis, Rich Strava, and Mike Curtis, called the keystone pathogen hypothesis, which is saying that an organism which may be present in quite small numbers might be responsible for the inflammation. That inflammation then may perturb the whole community and put it into what's known as dysbiosis. That's a non-normal community which is disease associated. And so they had some evidence from this from their mouse model. They took a mouse model, exposed the mice to P. gingivalis. In fact, P. gingivalis really didn't colonize well at all. Some mice, they couldn't find it at all afterwards. At best, they found it in very low numbers. But just that exposure changed the structure of the normal microbiota. The numbers of the normal microbiota went up, and then it seemed to be the normal microbiota itself which was associated with the bone loss in those mice. But that would only happen with a specific host genotype. So it seemed to have a susceptible host. Exposure to an organism may be enough to change the inflammatory status, which will in turn lead to the dysbiosis. And then you get into the ecological catastrophe, as Phil Marsh calls it, where you get this spiralling down where everything's going wrong and you result in periodontitis. So, to summarise what I said this morning, first of all, the new culture-independent methods have shown that the oral microbial community is extremely complex. In health and disease, we have a structured community which is characteristic for that particular disease. Hosted environmental factors are clearly of primary importance, so probably sugar consumption for caries, host susceptibility in factors like smoking for periodontitis. And what we need to do now for human disease is identify the keystone pathogens that are really driving the inflammatory process, which is at the heart of periodontitis in particular. So finally, I'd like to thank the people here who actually did the work I've described this morning from my group. These are my clinical collaborators here, my colleagues in Boston here, and here are the various funding bodies